Hello and welcome back to my channel. Today we're going to be talking about antiderivatives and indefinite integrals. So this first part we've kind of already talked about a little bit, but doesn't hurt to kind of repeat. So an integral is the area under the curve. We have two different types of integrals, definite integrals and indefinite integrals. Definite ones being the ones that have interval a to b, so a starting and ending value, versus an indefinite integral, which doesn't have our starting or ending value, which really just means it's like we're talking about one infinity towards the other infinity. One is generally going to give us probably a number versus the other one, which is going to give us an equation. So now that we've spent a little bit of time and we kind of know this notation a little bit more, we're going to be focusing on indefinite integrals here, just so that way we can kind of get used to doing what we need to in order to be able to find these values or equations. So when do we use an integral? When we see the integration symbol. So anytime we see the integration symbol, integral. If we need to find the position or velocity equation from the acceleration or velocity. So if I need to go from velocity to position or acceleration to position or acceleration to velocity, we need to use an integral. And then finally, if we need to find the area or volume of a graph or situation, areas go with integrals because they are the area under the curve or the area under a function. Volumes are going to be something that we're going to talk about in a little while that go along with this, but it's more of an application of what we're talking about rather than what we're talking about right now. So one of the things that you're going to hear about is called an antiderivative. It is the opposite of a derivative. Many times antiderivatives and indefinite integrals are interchangeable and mean the same thing. A lot of times it's really hard to find what's the actual difference between the two, and the biggest thing that I can see is notation-wise. We generally don't say something with the integral symbol is an antiderivative, and we don't really have a symbol for antiderivative like we do derivatives. So d over dx is our derivative, but we don't really have do the antiderivative like that. So we use the integral symbol. So in order to think about antiderivatives, we're going to think about derivatives first. So we have x to the second power. If we were to take the derivative of that, we are going to take the exponent, multiply it by the coefficient, so multiply the coefficient by the exponent, and then take 1 away from the exponent. I am messing up some of these letters today. Apparently I'm forgetting letters completely. So now that we've kind of thought through that, multiply the exponent by the coefficient, then subtract 1 from the exponent, we are going to be thinking about the opposite of this. And when we think about the opposite, we also need to do the opposite order. So whatever was last, we do first. So instead of subtracting 1 from the exponent, we're not going to be adding 1 to the exponent. And instead of multiplying whatever we have by the coefficient, we're going to divide our exponent by the coefficient. So we're going to look at a couple problems that kind of look like that, and we can kind of follow that same process. So the first thing we're going to look at is x. So we want to add 1 to our exponent and then divide by the exponent we have. So if I add 1 to x to the first, we're now going to have x to the second power. I want to divide by that new exponent, so I'm going to divide this by 2. So I can leave it as x squared over 2, or I can say it is 1/2 x squared. We have 2x cubed, so I'm going to add 1 to that exponent, so we have 2x to the fourth, and then we're going to divide this whole thing by 4. So I have 1/2 x to the fourth, or x to the fourth over 2. And then this last one, this one doesn't have an x already with it, so that means I know that it used to have an x and that it used to have an x to the first. So if I take the antiderivative of this, I'm going to get 13x. When I'm doing these kind of antiderivatives, one of the things that we're going to be thinking about is what derivative did we need to take in order to get that value we have. So in order to get a derivative that's equal to 13, I would have needed to take the derivative of 13x. If I had 2x cubed as my derivative, I would have needed to take the derivative of 1/2 x to the fourth power. So we're now kind of like working backwards from these derivatives. We're kind of doing them in the opposite order. So one of the things that we're going to be thinking about is not only like what is the derivative, but what's going on around that. So what is the derivative of 13x plus 7? Well, the derivative of 13x is 13. The derivative of 7 is 0. So we get a derivative of 13. If we look at the same thing, but 13x minus 54, we get the same kind of a deal, 13 minus 0, which is equal to 13. These two derivatives give us the exact same value. So when we look at these two derivatives, what do we notice? They give us the exact same value. But when I think about it as an equation, that is not the same equation. 13x plus 7 is different than 13x minus 4. So when I'm taking the antiderivative, like I did here, how do I know which version of this equation do I have? And that is completely dependent on what we call an initial condition. So without an initial condition, we will not know what version of the antiderivative we have. And when we talk about antiderivatives, we really are adding this extra thing called our constant. And this is where we are going to be adding a plus c. So we're going to add c to everything. So even if we don't know what the initial condition is, we know that we're adding some sort of constant here. It could be 0 for all we know, but we don't know for sure. So whatever we do, we're going to add plus c to it now. So if we have an integral, we're going to add c. Okay, so power rule for integration. We used to have power rule that looks like x to the n is equal to n x to the n minus 1. And it's going to look similar, but the big difference is what we're doing. So instead of subtracting 1, we said we add 1 to the exponent, so we get n plus 1, and we needed to divide by that exponent. So we're going to divide by n plus 1. And just like I said, we need to add a constant of integration every time, so we're going to add plus c to this. Our only requirement here is that n can't equal -1, and that's because if n equals -1, then we get 0 in the denominator here, and we can't divide by 0. So when we see n to the negative first power, we might need to do something else. Hint, hint, n to the negative first power is the same thing as 1 over n, so we might know what it is if we remember what gives us the derivative of 1 over n. So let's look at some problems that we have here. We have 13 minus x, so we're going to use power rule here. So I'm going to add 1 to our exponent and divide it by 1. So I have 13. That's an exponent of x where it's 0. So I know 13x to the first power divided by 1 is still 13x. And then we have a minus x. So we're going to add 1 to our exponent. So we have squared, and we are going to divide by it. Because I don't have an initial condition, I need to add plus c. Okay, we have 2x to the 5th plus 3x squared minus 1. So 2x to the 5th, we have 2x to the 6th, because we added 1, and then we're dividing by our new exponent of 6. And then we're going to add to it. We have 3x squared, so I have 3x cubed divided by 3. And then our last one, minus x. We have our constant of integration. I can simplify this, so I have 1/3 or x to the 6th over 3 plus x cubed minus x plus c. Okay, so we have the integral of x squared plus 1 over 2 times the square root of x. We're going to change what this looks like we would normally do for a problem like this. So the integral is now going to be x to the 1/2 power instead of the square root of x plus 1/2 times the square root of x when it's in the denominator is dividing by x to the 1/2. And in order to get it out of the denominator, we're going to make it a negative exponent. And then dx is our width of our rectangles. It's that change in x, so we kind of just need it as this. What are we taking it with respect to? All of these different things are going to be with respect to x in this particular case. So same thing, add 1 to our exponent and divide by it. So x to the 3/2 power divided by 3/2 plus 1/2. We have x to the negative 1/2, which then would give me x to the 1/2 divided by 1/2 and plus c. If I'm dividing by a fraction, it's the same thing as multiplying by the reciprocal. So I have 2/3 x to the 3/2 plus we have 1/2, and we're dividing by 1/2. So 1/2 times 2 over 1, that's going to give us 1. So we have 1x to the 1/2 plus c. So I could write it as 2/3 times the cubed root of x squared plus the square root of x plus c, but we can also leave it like this. And then our last one here, for what we're doing right now, we want to rewrite this. So I have the integral of, and I'm going to divide each term by x to the 4th. So I have x to the 4th divided by x to the 4th minus 3x squared divided by x to the 4th plus 5 divided by x to the 4th. X to the 4th divided by x to the 4th is 1 minus 3 divided by x squared. That's going to give us x to the negative 2nd power, and I can get that from 2 minus 4. And then this last one, we have plus 5x to the negative 4th power. And then what we're going to do is actually do our integral now. So if we integrate 1, it's going to be x minus 3x. If we add 1 to negative 2, that's going to give us negative 1. Plus 5x. If we add 1 to negative 4, it's going to be negative 3. And then our constant of integration. I can clean this up a little bit. So we have x. We have minus a negative, and it's being divided by 1. So we have plus 3x to the negative 1st power. Minus, because we have plus a negative, 5/3 x to the negative 3rd plus 3, and I can move these down, so I could write it as x plus 3 over x minus 5 divided by 3x cubed plus c.